In this video, we'll begin to look at sampling distributions, concentrating on sample proportions. We've talked a lot about probability recently, and it's time we start putting it to use, seeing how probability informs what happens when we collect and analyze our data to make conclusions about a larger population. Speaking of population, do you happen to know what percentage of the human population is left-handed? Turns out it's about 10%. Maybe you're even one of them. This is something that we call a population proportion. About 10% of all the people in the world are left-handed. We usually represent a population proportion with the letter P for proportion. Now, if we take a sample of people and we figure out what proportion of that sample is left-handed, that's called a sample proportion, which we usually write as P with a little hat over it, and we call it P hat out loud. For example, if we sample 20 people and 2 of them are left-handed, then P hat equals 2 out of 20, which comes out again to 10%. It seems pretty reasonable to believe that if 10% of the population is left-handed, then 10% of the sample should be left-handed. But that's not always the case. Depending on what sample you happen to pick, you might get more than 10%. Or other times you might get less than 10%. There's a lot of variation. Wait, hold on a minute. Think about everything we just said, talking about the variability of P hat and the fact that it could come out different every time we pick a new sample. That's exactly the sort of thing we use random variables to describe. Picking a random sample of people is a random event. So the proportion of left-handed people we get can also be modeled as a random variable. Since taking samples is so important in statistics, it should come as no surprise that the distribution of a sample statistic, like P hat, is called by a special name. We call it the sampling distribution. Let's take a closer look at this sampling distribution. I went ahead and used Microsoft Excel to run a simulation of picking 100 random people. That's a sample size of n equals 100. You'll see why I chose that number soon enough. Assigning a 10% chance that the person is left-handed, and then counting up how many left-handed people I got each time. I ran this simulation 50 separate times, each time counting up the number of lefties and putting them into the table that you see here. Now, if we divide each of these by our sample size of 100 to get our sample proportion, and plot the results on a dot plot, here's what we get. As you can see, we have a peak right at 10%, since 9 times out of the 50, we got 10 lefties, and 10 out of 100 comes out to 0.10. Now, if you look at this and kind of squint a little, you might notice that it's roughly symmetric and unimodal, with lots of points toward the middle and few towards the sides. Look familiar? If you squint hard enough, you might think that this looks roughly like a normal distribution. And you'd be right. In fact, this resemblance to the normal distribution is an example of what we call the central limit theorem, which essentially says that if you take independent samples with a large enough sample size, the sample statistic tends to be normally distributed around the true parameter we're interested in. In this case, our true parameter is the real proportion of people that are left-handed. Now, what do we mean by a large enough sample size? How large is large enough? That kind of depends on the situation. But when we're looking at proportions, we can apply the central limit theorem when both n times p and n times 1 minus p are at least 10. In our case, the sample size was n equals 100, and the population proportion for left-handed people was 0.10. Then n times p comes out to 10, and n times 1 minus p comes out to 90, so we're in good shape. Literally. The central limit theorem says that our sample proportions generally follow the shape of a normal distribution. We can even say exactly what the mean and standard deviation of that normal distribution should be. The mean of our sampling distribution will just be P, the population proportion. In our case, that was 0.10. So that tells us that if we keep taking new samples, we should expect the results to kind of hover around 10%. Sometimes we'll get more, sometimes we'll get less, but on average, 10% of our sample will be left-handed. The standard deviation of the sampling distribution is admittedly a bit more complicated, but not much. Just multiply p times 1 minus p, divide by the sample size n, and finally take a square root. If we work this out for our left-handed problem, assuming a sample size of 100, we get 0.03 or 3%. That tells us that on average, we may be off by 3% in either direction when we take a sample of 100 people and ask how many of them are left-handed. By the way, the standard deviation of the sampling distribution is sometimes called the standard error, or SE for short. You'll see why a little later in the course. So with this data in hand, we can use everything we've talked about with the normal distribution to make conclusions about the values we might get for the sample proportion. To close out, here's some food for thought. You often hear people talk about how having a large sample size is better than having a smaller one. How can we use what we've talked about in this video to show why that's true? In other words, what effect does the sample size, that is n, have on the sampling distribution? If we make n larger, what does that do to our normal distribution? Think this over on your own.